Thanks, everyone. So, hey, I'm Dustin. Quick intro about me. So I'm a developer advocate at Google. That means that I represent the Python community internally at Google when we build products for Pythonistas. I'm also the chair for PyTexas. By the way, it's going to be in Austin this year, or next year, sorry, May 16th and 17th. So you should come to Austin, come and hang out, go to PyTexas. I also work on the Python package index, critical Python infrastructure that I'm sure you all use. But I'm not actually going to talk about any of those things today. So we're going to talk about static typing. Quick pop quiz for everyone in the room. Is Python dynamically typed or is it statically typed? So who thinks it's dynamically typed? And who thinks that, like, all right, this talks about static typing in Python, it's probably statically typed? Maybe. How about, who thinks this is a trick question? Okay. It's kind of a trick question. The answer is that Python is dynamically typed, but can optionally be as statically typed as you want it to be. So the answer to that might not actually make a lot of sense if you're not super familiar with typing and type systems. So that's okay. That means that you're in the right talk if that doesn't make sense to you, and we're going to explain that. And the steps to understand and answer that question are basically this. We're going to talk about types in Python, type systems in general, dynamic typing in Python, and then static typing in Python. And then once we sort of understand what static typing in Python means, we'll talk about how to use static typing, when you should use it, and when you shouldn't use it. So let's talk about types, and specifically let's talk about type. When I say type, I mean the type built in your Python interpreter. So in your Python REPL, you could type something like this, type 42. And this will tell you that 42 is an int. It's an integer. You can also type other things. So the type of 42.0 is a float, type of foo is a string, type of that is a list. And you might say, OK, I recognize these things that are coming out of the type function. These are like the built-ins that I can use to change one type to another, right? So you can take an integer, like a here, and you can, sometimes we call this casting, cast it to a float, cast it to a string, cast it to a really ugly list. So who's seen a really ugly list like this before, where a string is getting turned into a list, right? OK, if you've seen that before, that's a type error. You've had a type error in your code, and something that was expecting a list got a string instead. So it would also seem like these are the only types available to us, but that's not entirely true. So these are just basically some mappers to classes that exist. So int here is just a class. So I can say the type of 42 is an int. I get a class of int from int, and is instance 42 int is the same thing as doing class matching if something is an instance of another class. So there are more types than just int, string, float, right? So there's none type. We've all seen none type before, but you can only get it by calling type on none. There's also a function type. So when we define a function, we don't say like function, blah, blah, blah. We say def, function name, et cetera. And there's like an ellipsis type. There's lots of types. And in fact, if you are in your Python REPL and you import types, you get this whole list of all sorts of types of things that you could have in your Python code. And so these all live in the types module. And they actually can be used to instantiate a new thing, like whatever this is. You can call open close parentheses on it with some arguments and create a new function type. But there's a reason we don't do this. It looks really messy, and there's like a lot of code to it. So when we say Python is a dynamically typed language, what it means is that variables can be any type at all, and they can change. So for example, if I imported random, and I call it random.choice on this list of things that are an integer, a float, and a string, and I call type of the result of that, what's the result? Like, what type is A going to be? It could be any of these, right? It could be a string, an int, or a float, and it depends on the outcome from random. So it doesn't matter what I'm putting in that variable. It can contain any of these types. Dynamic typing also means that the arguments and the return types of functions can also be any type, right? So the same is true for the arguments and the return values of any function. So if I create a function like this, frobnicate, takes three parameters, a, b, c, returns a plus b plus c. So in Python, when we write a function like this, how do we know that we're getting the type that we're expecting out of it, right? So if you saw this function and you had no idea what frobnicate meant, because it's a made-up word, what would you expect the arguments to be here? And what would you expect the return type to be? So you might say, like, it might make sense for these to be integers, right? So I define the function, I can call frobnicate 1, 2, 3, and I get 6, the sum of all these integers. But also I could call frobnicate with strings. I can call frobnicate with 3 strings, and it would concatenate those strings. That's totally valid, and it totally works. The function can return integers or strings. However, what I can't do is I can't mix these types now, because I can't actually use the plus operator on a mixture of strings and integers. So that blows up, and that creates a type error. So it'd be great if we could say what this function actually is expecting for all these arguments and what it's expecting to return. So one thing we could do is write a really long and nice doc string that lists all the arguments and the return types and what they are and some comments. Who does this? Does anyone do this? Does your employer pay you enough to do this? This takes a lot of work, right? It's a long comment, and you got to write it all out. It also doesn't actually change the evaluation of the function, right? You can still call this with strings, and it's still going to return a string. It's just a little handy guide there for the developer. We could do this. So we could write a function. We could assert on every single argument that we get, do our business logic or whatever we need to do, and then assert on the return type, and then actually return it. I said in a previous talk one time, I showed this example, and I said, yeah, nobody does this. And then someone came up afterwards, and they're like, well, actually, we do. do this. And so the reason you don't want to do this is because each assertion, while this works, each assertion adds just a little bit of overhead to your function call, right? Because that happens at runtime, each assertion. So while it's modest, there's a small performance problem there. And also, it's a little bit messy looking to have all those asserts all together. So we don't really do that. What do we do instead? In Python, we do something called duck typing. So instead, duck typing is, if it walks like a duck and it quacks like a duck, it is probably a duck. So we sort of observe the way that we interact with functions and variables, and we can sort of infer what the types are from that. So for example, in these examples, right, I'm setting foo to list comprehension, calling f of x on x, and bar is probably some iterable. It's something like a list or a string. And the second line, foo, is bar greater than 0. So bar is probably an integer, something I can compare to an integer, and foo is going to end up being like a Boolean. And then the last one, bar, is something I can call open close parentheses on. But that means it could be a function or it could be a list. Like, it's still actually kind of ambiguous what this is. And usually if it was a class that I was calling, or sorry, it could be a function or a class. If it was a class, bar, we'd probably capitalize it, but not always. It's not required. So it could be anything. So static typing means that these variables and the return types and arguments to function are not going to change. They're defined what the type is going to be, and it's not going to change. And so there are actually a lot of statically typed languages. So I want to show you some examples of that same function, that for obfuscate function, in multiple languages. So does anyone know which language this is? I heard it. Yeah, C. That's C. How about this one? Java. Yeah, that's a dead giveaway with like public static in. Anyone know what this one is? Yeah, every time I do this talk and the Rust one comes up, I was like, yeah, that's Rust. I know Rust. Yeah, that's Rust, because Rust actually has really fine grain. That's an unsigned 8-bit integer for the argument types there. So you can say exactly what type of integer it is, not just an integer. How about this one? Anyone? I heard JavaScript, but it's actually TypeScript. It's typed JavaScript. The way you would know is that JavaScript actually has only one number type. It's number, like floats and integers, everything is a number. Okay, so you can sort of put languages in two columns, right? Dynamic languages are like Python, Ruby, Clojure, and JavaScript. Static are like C, Rust, and TypeScript. And actually, you have to put, like a little asterisk next to Python, and we're going to talk about why. Because you can do some static typing things in Python. And also, technically, Ruby is going to also get the same thing that Python currently has, but not until the end of next year, so we'll ignore that. So, like earlier I said, Python is dynamically typed, but can optionally be as statically typed as you want it to be. So the story of that becoming true, that wasn't always true, right? There was a point in time when Python was purely a dynamically typed language. And the story of Python becoming a language you could optionally statically type is also kind of the story of the evolution of code at Dropbox. Does anyone work at Dropbox here? No. Okay. So Dropbox is a large tech company, and they're a Python shop also, and they have millions of lines of Python code. And basically, at a certain point in their evolution as a company, they realized that the fact that their Python code was lacking any kind of type system or type annotation was actually slowing them down. Like, it was causing their developers to be less productive when they were looking at code, because there was so much of it. It was so intertangled. There's so many different areas of the code base. And so they actually wrote a blog post. You can go and find it on their blog. It's super good, and it talks about sort of a little bit about the history of static typing at Dropbox, but I'm going to actually talk about the history of static typing in Python, which steps back a little bit from the start of it at Dropbox. And so the start of it in Python starts here at PEP 3107. This is the functions annotations PEP. We got this in 2006, and only in Python 3. And what this allowed us to do is take a function like this, which is the same one I showed before, and then we can add annotations, any metadata that we want, to the arguments and to the return type. So these aren't types. This is just like literally any Python code you want, you could put in the annotation for this function. And this has zero effect on the execution of the function. What it does instead was it gives you this annotations, dunder annotations attribute. And what it would do is evaluate the value of all those annotations. It would execute the annotations. And so here it would say, like, OK, A has this annotation of a string of X. B, I've added 5 and 6, so now it's 11. C, and then the return annotation. So this is interesting. And in the PEP, they sort of outline some uses for these annotations, right? So all of the uses kind of basically boil down to, you can do interesting typing things with it, and then also like maybe, or you could use it for documentation, but you probably should use it for types. But it didn't really specify a way to use it for types. But we could imagine doing something like this with it, where in the annotation, we just put the type there, right? We say A is an int, B is an int, C is an int, returns an int. And so when I look at the annotations, I see what all of those are supposed to be. However, just because I can annotate a function, again, doesn't mean I can actually evaluate whether that function is being used correctly elsewhere. Like Python is not going to look at these annotations at runtime and figure out if they're right or wrong or it's being called correctly. So it only gives us a way to annotate this function, and actually only functions too. I can't annotate variables with this. It's only for functions. So a little bit around the same time, Jukka Lahtasalo was working on his PhD thesis at University of Cambridge. And his PhD thesis was about this. It was about the unification of a statically typed and a dynamically typed language. Basically, how could you have a language that had both? And the goal was to be able to use the same language for everything from a tiny script where you don't really care about typing that much to like a sprawling multi-line code base where, like Dropbox, you start to actually care about typing. And he had this idea of gradual growth where you could go from something that was untyped and slowly add type annotations optionally where you needed it until you had something that was fully statically typed. So he published a paper, his thesis in 2011, and in it he concluded this. He said that adding a static type system to a dynamically typed language could be a totally invasive change, requires coordinated modification of like everything, basically. The program, the runtime, virtual machines, all the tools, everything. He also said that you could optionally do an optional pluggable type system that doesn't actually affect the runtime of the program and is basically a layer on top of the program and wouldn't require this modification of all of the existing tool sets. So this sounds really great. Without having to change Python would be awesome. So in 2013, he gave a talk at PyCon US, and he introduced something called MyPI. So if you are familiar with MyPI, this is probably not what you're familiar with. When he introduced it at the time, this is what MyPI was. MyPI is an experimental variant of Python that supports writing programs that seamlessly mix dynamic and static typing. So this was not what you think of as MyPI now. MyPI you think of now as a static type checker. At the time, it was actually a variant of Python itself. It was its own language. And so in his research, he didn't even use Python as an example. He made up a language sort of as a toy language to show that this was actually possible. So MyPI, the language, actually looked like this. And it kind of looks like Python. It was definitely inspired from Python. But it had some extra stuff to allow him to do variable annotations and better function annotations. Because at the time, all we had was function annotations. So he gave this presentation at PyCon, and he said he gave the presentation and he talked to Guiteau about it, and Guiteau's like, yeah, just ditch the variant language. Like, let's just do this in Python proper. And so he said, okay. So he convinced him to drop the custom syntax and stick to just Python 3, where we have function annotations, and we can do some other stuff as well. So in 2014, we got PEP 483, and this was Guiteau writing down basically his theory of type hints, like how typing should work in Python. So there were some big ideas here. One was, sort of drew from Jukka's paper, one was optional typing. Adding annotations to the runtime shouldn't affect the actual runtime of your program. So like I said before, an unannotated function should run exactly the same as an annotated function. And I think this sort of distills from lessons that we learned in the Python 2 to 3 migration, right? We don't want to introduce this huge breaking change across Python versions. We want it to be sort of like gradual and available if you want it, but not going to get in your way. The other was gradual typing. So let's not try to do this all at once, right? Typing a giant code base is going to be impossible to do all at once. You should be able to do little pieces at a time. He also introduced the idea of variable annotation. So this was building on the idea of function annotation so that we could annotate variables as well. And so that would mean that we could have a function like this, and we could add a little comment that says the type of this variable I've just defined is an integer. This also meant that we could do type hinting in Python 2. So the syntax for function annotations only came in Python 3, but because even those on like a super old version of Python still deserve to be able to do static typing, we were able to take these type comment annotations and backport them to Python 2 and sort of get the same behavior. So in Python 3, we could actually put them in line with the function annotations. In Python 2, we could just write a comment underneath the function declaration and have the type annotation there. He also introduced some ideas for special type constructs. So these are building blocks that we actually need to do typing that aren't already available in Python. So these are things like any. Any is a type that matches literally anything. Union would be, this thing could be a type of one type or another type. Optional means that it's an alias for union of some type and none. A tuple would be a tuple type with specific types inside of it. A callable is similar. So this means that we could define a function like this, where fromnicate takes an integer, but the last argument could be a float or it could be an integer. And the same thing for the return type, right? So this would allow us to statically type this function and actually say exactly what those arguments would be. It also defines some container types. So these would be like a list or a set. And this allows us to sort of say like, okay, I'm initializing this list and it can only contain integers. Or I'm initializing this dictionary and the key is a string and the value is an integer. And so that would cause the type checker to either pass or fail in the various situations. It also defines some generic types for when a class or function behaves in a generic manner. So that would be like an iterable, right? If I just want to say like this function takes anything that I can iterate on, like a string or a list or whatever, I can just call it an iterable. It's generic across all types. It also defines the relationship between types, subtypes, and classes. So like I said before, a type is basically just a class. So like when I did this before, we just get a class out of it. That means that I can define a class as well, and that just becomes a type. So when I instantiate a foo here, I just get the type, which is the class I used to instantiate it. So for int, like int is both a class and a type here. I can create this another class like user ID. This is still a custom class, but also still a type. And then it's important to note that things like those special type constructs are not also classes that we can instantiate, right? You can't initialize the union of a string and an integer. It doesn't really make a lot of sense. And we can define type aliases. So this is nice if we want to just like pretend like we're JavaScript and have a number type that just is every single number available to us. And then after he did PEP 43, he did PEP 484. So this is type hints, and this basically standardizes everything in PEP 483, and it basically standardizes on what MyPI's behavior. And at this point, MyPI is kind of like just the type checker. And so PEP 484 is how to build a type checker for Python. And this was all released in Python 3.5 in 2015. So it had PEP 484 support, it had a typing module that we could import from, get those special type constructs. And then we kept going. So in PEP 5.26, we got syntax for variable annotations. So using the comments in Python 3 felt kind of janky, and it also had some problems. So like I said before, you could initialize an empty list and set the type on that list. It was kind of messy when we tried to instantiate something that we didn't want to set to a value yet. We kind of had to give it an initial value if we wanted to type it. And so the variable annotations let us do things like this. We put the annotation in line. If it didn't have an initialization value, we could just set the annotation and just not initialize the variable at that point. And the same is true for like class variables. We had like the ability to instantiate class variables and things. That was available in Python 3.6. And this almost had everything we needed to do static typing in Python, except we needed a type checker. So this is the last piece of the puzzle. And at this point, we have MyPI, but there are also other static type checkers available as well. So there are two types. Static versus dynamic. So static type checker is going to run while your code is at rest. It's going to actually run across your static code base and infer all the types from your code A dynamic type checker is going to sit with your code at runtime and infer types, kind of like those asserts that we were doing before. So most of the type checkers I'm going to talk about are static. So by this point, MyPI had become, like, it's no longer a variant. It's a tool that's a type checker that's released on MyPI. And you could run it like this. You could pip install MyPI. I could define some file that has some bad typing in it, and I could run MyPI on that file, and it will say, OK, you've said that these 3 arguments are integers, but you're calling them with strings. This is a type error, and I'm going to give you a warning. So there's lots of static type checkers, like I said. They all support and implement PEP 484. So there's MyPI, that's mostly supported by Dropbox at this point. PyType is from Google. PyR is from Facebook, PyWrite from Microsoft. PyCharm actually has its own built-in static type checker, which is kind of cool. But also, like, you can integrate your editor, whatever your editor is, with all of these other type checkers as well. And then there's a bunch of dynamic ones, but again, they have some overhead at runtime, so they're not generally preferred, I think. So disclaimer, I work at Google, so I will talk about PyType just a little bit too. It's also available on MyPI, and the inevitable question between when you're looking at all these type checkers is like, what is the difference between them? And since they all implement this PEP, this standard, like what's the actual difference here? So the difference between MyPI and PyType, there's basically 2 things I'm going to point out. One is what I'll call cross-function inference, and the other is runtime lenience. So they basically have 2 different philosophies about when they should raise errors. So cross-function inference means that if I define a function and one function returns a string and the other tries to take the output from that function and do something that would be a type error at runtime, if I run this example, it's going to raise a type error. If I run it with MyPI, nothing happens, because MyPI doesn't actually have the ability to infer across functions that one function is going to return a string and the other function is trying to use that as a string. If I run it with PyType, though, it will raise an error. It will say, this is going to produce an error when you try to run this function. You probably want to fix it. The opposite is that MyPI is going to be really strict when you define its types, but PyType is going to say, if this doesn't actually produce a runtime error, I'm not going to raise a problem. So here, I have a function that's supposed to return a list of strings, but in the function, I'm appending an integer to it, and I'm returning that. MyPI is going to look at this and say, this list is supposed to only contain strings, and you're putting an int in it. So when I run this, like, it works totally fine. PyType is going to say, yeah, no problem, that's not going to create a runtime error. But MyPI is going to raise an error and say, you tried to do something to this list, and I thought that it was going to have a different type. All right, so why? Why and when should we use static typing? So first I'll say when you shouldn't use static typing. Basically never. There's not really a point in time when static typing is going to hurt you. Again, it's like optional, and it doesn't affect the runtime of your program. The one time that maybe you shouldn't choose to use static typing is to replace your unit tests. So there is sort of a school of thought here that sometimes you write unit tests and they kind of just look like you're doing type checking, right? You're making assertions on the way you're calling the function. And that's kind of true, because unit tests are, in some ways, kind of like a bad type system. But in reality, like, don't replace your unit tests with static typing. You probably should just do both here. So when should you use static typing? Basically, use it liberally. Use it as much as possible. It's good for you. So you should use static typing when you're millions lines of scale. So I'm not sure anyone's code base is currently millions lines of scale right now here. But basically, Dropbox found that when you're at that scale, that Python, it's actually a liability that Python is not statically typed. The overhead to understand that much Python code that doesn't have type annotations is so high that it actually affects productivity. So that's why companies like Google and Facebook and Microsoft and Dropbox have all invested in these type checkers and have started statically typing their code, because it actually is worth doing for them, because they have millions of lines of code. So basically, like, there's this graph that you can imagine, where as your lines of code go up, your desire to add type annotations increases, but your ability to add the ease of adding it goes down. So you're all probably here, maybe. You should migrate and add static typing probably about here in the graph. That's when it's easiest. This is when you're probably going to do it, but that's OK. You'll still be able to do it anyway. You should also use static typing just like when your code is confusing. So let's be honest, everyone has written some confusing code at this point. It has been said that annotations are basically like machine-verified documentation, right? It's something that your developers can look at and understand what types are available to them in their function. But also, you can run a type checker on it and verify that that's actually the way it's being used. So if you feel like you need to document the input and output types of your function or your class or whatever, that is a good indicator that you should probably just add some static typing. You should use static typing when your code is for public consumption. So like if it's a module you're going to put on MyPI. Adding type annotations help developers know how to use your API. Also helps your IDEs figure out how to do auto-completion and things like that. And then also if your users are doing static typing in their code and they want to use your library, they're going to love it because the static typing is going to be available to them as well for your code. You should use static typing before migrating or refactoring. So add some static typing in a place where you're about to do some refactoring, and then go make your changes and then run your type checker and make sure that you're still calling everything in a way that's consistent with the types that you had set up before you did that migration. You can do static typing just to experiment with static typing too, right? Like I said, it doesn't hurt. You can try it out now if you have a modern version of Python. Yeah, it's totally valid to just experiment with it. And finally, you can use static typing if you're just cold. Gary Bernhardt says static types are a warm blanket that I have missed so much. And by the way, Gary's background on Twitter is like the best thing right now. Here lies Gary, stung by type errors. All right, so to wrap up, how to use static typing in Python in just 5 easy steps. So first, you could, this is optional, but you could migrate to Python, modern version of Python. You can do type annotations, type comments in any Python version. You can still do it in Python 2. But in Python 3.6 or above, you'll get variable annotations, function annotations, and everything else as well. And you should probably be migrating anyway, let's be honest. You can install a type checker locally. I don't care which one. You can install multiple ones if you're interested in trying out multiple ones. Yeah, install it locally and integrate it into your editor, right? You can actually make it so that the type checker will run whenever you open a Python file in your code and just check out that file. And as soon as you start adding type annotations, it will start telling you if you're using them correctly or not. And then you can start optionally typing your code base, right? Start with maybe like your most confusing and hairiest files. You can start with the easiest things to type check as well. Remember, you don't have to do it all at once, so you can just start in some place, do it gradual, pick the critical areas and start there. And then once you get to a point where you have some type checking in your code, you can run type checker when you lint your program. And finally, convince all your coworkers to join you in static typing. If you need help convincing them to join you, you can show them this talk on YouTube. So thanks, everyone.
Thank you, Dustin, for your talk. You're an excellent speaker. I wish I could travel the country to listen to you talk. I accidentally found static typing the other day. I found out that I had to import the class in order to statically type a function, and then I got a recursive import error, and I realized that when I start to import all of the types across all of the application to statically type all of the functions, I was probably going to get a lot of, I think they're called recursive import errors. I was wondering if you have any thoughts on that sort of import and recursion mess.
So the issue is that you have some custom types, some classes and stuff defined. You have it in your code, and you need to import it to define the types in some function, but it hasn't actually, you're doing a recursive import. So the one thing I will say about when you start to add static typing to your application, it does sort of indicate to you which parts of your code base are not very well written. I'm not saying that you've written bad code, but it will, when you sit down to annotate a function, and you're like, man, this is really hard to add the typing. I'm confused, and MyPI is really complaining about it. I can't get it right. It probably means that function is not well written. The arguments are ambiguous, or it's receiving more than it should or not. Specific to circular imports, so what you can do in MyPI, and in all the type checkers, you can use strings instead of the actual classes themselves. So yeah, if you have circular imports like that, you don't actually need to import them to define the type for them. You can use a string instead. And then it also sort of depends, a lot of it depends on the way your code base is structured, but yeah. That's a great question.
Any more questions? Yes, if you can make it a really brief one, because we want to go for lunch. And And then you guys can always talk to him in the hallway.
Cool. Yes, thank you very much, Dustin, for your great talk. I'm a big fan of the static typing in Python. How do you feel about Django? And personally, when I've used the typings, I've used a plugin called MyPI Django to bring in the types.
Yeah.
I'm not aware of any motion, but I'd like to see the types in the Django code base. Would you agree? And is there an initiative to get that moving?
So I'm not like really, I can't say this too loudly, but I'm not actually really a Django developer. I'm a Python developer. I do know a little bit about what static typing looks like in Django. So I think there is some ideas maybe about adding static types to Django codebase itself. But the nice thing that I didn't mention is that, so Python, the folks that work on MyPI also ship this project called TypeShed, and that's type annotations for everything across the standard library. Basically, you can add type annotations external to any third-party package or library. So there is a project, I am forgetting what it's called, but it's basically like Django type annotations, a third-party project that has type annotations for a significant portion of the Django code base for a specific version of Django. So that is something that you could use to get these type annotations for Django. From what I have heard, there's some magic happening inside of Django that causes it to be difficult to do type annotations, basically the way that models and things are defined. So my understanding, and this is like a very high-level understanding, is that it is sometimes challenging to add type annotations to some parts of your Django application. But generally, I mean, you can use it in non-Django-y parts of it as well, right? Like you don't have to exactly type everything in your code base in order to get the benefits.
Cool.
Yeah.
Thank you very much.
Thank you. Thanks for the question.
All right, let's give another round of applause to Mr. Dustin.